Welcome, everybody. Thanks so much for coming out tonight. What a beautiful night. You could see the stars, and it wasn't 35 miles an hour like it was supposed to maybe be. You all are a wonderful group. A lot of you are here because of the organization, so thanks to all the organizations that came tonight. Really, really great. Really appreciate it. We have a lot to be thankful for. Dr. Holloway's here, and she's been all over the place giving talks, a renowned researcher, so we're just so lucky to have her here. If we think about a big picture a little bit, and think about appreciation of where we are and when we are, and you think about the universe, now we can see out into the universe. We can see all these galaxies that are many, many light years away. There's a lot of space. Billions of galaxies. And then we've got our own little galaxy, the Milky Way. And we're kind of on the nub side of it. We're a little bit out from the center. And then we've got our solar system. And then we have our sun. We're about 93 million miles away from the sun. We're at a perfect distance. If we were closer, we'd fry. And if we were farther away, we'd freeze. We're at a good time, too. We have ecosystems that have developed over millions of years. You know, there used to be trilobites running on the ocean floor right where we are. And I don't think probably too many of you got ambushed by a T-Rex on your way here. Mammoths aren't here anymore. Things have changed a lot. And the ecosystem that's here now is precious. If you look over your right shoulder and up a little bit, there's a little dot in the distance. That's us. That's the Earth. At pretty close to relatively the right size. Not too far away from the sun, not too close. We're in the right time. And I think we all appreciate it. And that's why what Dr. Holloway has to say is so important. To introduce Tracy Holloway is Associate Professor of Biological Sciences, Carrie Wren.
Thank you, Bob. I'm pleased to introduce our speaker tonight, Dr. Tracy Holloway. She's the Jeff Rudd and Jean Bissell Professor of Energy Analysis and Policy at the University of Wisconsin-Madison. Her background includes a bachelor's degree in applied math from Brown University, a PhD in atmospheric oceanic sciences from Princeton University, and a postdoc at the Columbia University Earth Institute. She started at Madison in 2003 and has a joint appointment there in the Nelson Institute for Environmental Studies and the Department of Atmospheric and Ocean Sciences. This provides a platform for the interdisciplinary work that the Holloway Group does at the intersection of air quality, energy, climate, and public health. Dr. Holloway serves as a team leader for the NASA Health and Air Quality Applied Sciences team, working on air quality management and public health. She's a co-founder and was the first president of the Earth Science Women's Network, ESWN. She's also the first ever recipient of the MIT C3E Award in Education and Mentoring. Dr. Holloway strives to make understanding climate change accessible to all. She's a founding member of Science Moms, a group of climate change scientists who help demystify climate science for everyday people. It's essential that we all have a better understanding of climate change and how to combat it. Tonight, Dr. Holloway will help us to do this as she tells us about solving the climate challenge, lessons from the past, planning for the future. Please join me in welcoming Dr. Tracy Holloway.
Well, thank you all so much for being here this evening, and thank you to Bob and Carrie for those lovely introductions. This is my first time visiting this campus, and it's just such a pleasure to be spending the evening talking about this important topic. So I did not know about this diorama of the sun and the earth, but it's a very good setup for the first slide, which is what you would see if you were on the International Space Station, orbiting the earth and looking out at the earth. And to me, this perspective really helps see that this thin layer of the atmosphere is what is keeping our planet habitable. And so I've really dedicated my career to understanding what are those chemicals in the air and how can we make sure that they are being monitored and managed in a way to maintain a healthy and stable planet system. So I'm going to start out thinking back to this summer to some of the smoky days that were so unusual for us to experience here in Wisconsin. And from here in Janesville across the whole state, there was really this unprecedented awareness, coverage, and really levels of air pollution. And I always like to look at this data not just from the ground, but also from space. And as it was mentioned, I work leading the NASA team to make satellite data more relevant for public health and air quality management. And it's pretty amazing that there are satellites up in space that can see chemicals in the air, even chemicals that we can't see with our eyes. Now, of course, with the smoke this summer, we definitely could see it with our eyes and smell it. But some of the imaging from the satellites can help us see where it was coming from. And while we can't have images under the clouds, so where you see white, those were clouds, we do see the reds showing high levels of particles in the atmosphere, just what you would expect from wildfire smoke. And we had a few different smoke events through the summer, but the worst was on the 27th and 28th when we were at the crossroads of smoke coming from Western Canada and from Eastern Canada, as you can see here in these images. At the time, there was a lot of press coverage saying, is this climate change? Is this climate change? And the truth is, we have had smoke from Canada over the years. It's just a typical part of summer. But it was not typical, the number of days and the severity of days that were this past summer. And in fact, across the United States, wildfires are becoming more and more common. And this was something that's been predicted for decades as temperatures were projected to get warmer, land was projected to get drier, and the occurrence of wildfires were expected to spread. And while the summer event affecting us was from wildfires in Canada, I pulled some data here about wildfires in the United States. And what you can see is that going back to the early 80s, there has been this steady upward climb in wildfire extent. And that's driven by drier conditions across the West. The two different lines here is just different ways that the federal government is tracking data. The Forest Service stopped tracking data in the mid-90s, but it compares pretty well with the data that kept going. This is another way to look at that drying conditions across the West. And this is the change in precipitation, or I should say dryness of the land, drought, across the United States from 1900 to 2020. And what you see is that here in the Midwest, we've actually been getting wetter. But across the West, where we have these fires breaking out, it has gotten drier and drier. And even though I'm not going to spend too much time talking about precipitation and rainfall, it is such a big issue that I just wanted to zoom in to think what has been happening here in Wisconsin and to show that not only has our overall rain been increasing, but also the number of days with really heavy precipitation that can lead to flooding. And this is the number of days with precipitation of 1 inch or more. And again, in this case, going back to 1950s. But thinking about what happened this past summer and how unusual it is, I really like this kind of plot that you're looking at here. I love plots. That's what scientists do. But what you're seeing here, each little line is 1 day's worth of air quality. And these color codings are based on the EPA's designation of whether it's unhealthy for sensitive groups, which is orange, or unhealthy for everyone, red and purple, or green, meaning below the standard that the EPA sets as a health-based standard. There are two main pollutants that are affected by wildfire, but here in Janesville, you only have one of the pollutants monitored for ozone, so I pulled that for you here. And what you see is going back to 1980, which is the latest that this plot goes back, that there used to be quite a few yellow days, quite a few orange days, quite a few red days. But they've been getting fewer and fewer and fewer over time. And the reason is because there have been regulations put in place on the ingredients that form this ground level ozone, sometimes referred to as smog. And those two ingredients are nitrogen oxides, volatile organic compounds. These come from a wide range of sources, cars and trucks, electricity, industry, and there have been measures that have been put in place. Our cars are getting cleaner, our trucks are getting cleaner, our power plants are getting cleaner, and as a result, we don't have as many unhealthy days. In fact, if I had been giving you this talk a year ago, I would have just said it is just a good news story. It's getting more and more green, 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 green. Until 2023. And if you look at 2023, you have had red days and orange days more than really any year, maybe the early 2000s, really more like the mid-1990s or the early 1990s. So what happened this summer was very unusual. And what it's doing is it's setting us back on the clean air progress that had been a success story, and really is a success story, I'll make the case. So when we're thinking about what climate change looks like and what are some of the negative impacts, one of them has to do with this connection between the air we breathe and how healthy it is for us to just go for a walk or take our kids to the playground. But this is a good time to pause, and I'll put on my professor hat and introduce three different topics that are often confused. So first I want to lay them out as three totally different topics, but over the course of the next hour, we'll be weaving them together, hopefully in ways that share some good news stories and strategies to move forward. The three big topics that have to do with environment, policy, sustainability, environment, atmosphere, terms that we'll be using are air quality, the ozone hole, and climate change. And when I talk about air quality, I am referring to chemicals in the air that make people sick, reduce life expectancy, reduce crop yields, harm ecosystems, impact visibility, just kind of bad stuff in the atmosphere. And these chemicals in the atmosphere have actually been regulated in the United States since 1970 through the Clean Air Act. And in many ways, air quality in the U.S. is a success story. I'll show you more about that in the next couple of slides. The ozone hole is dealing with the same chemical that I just showed you, ozone, but way up high in the stratosphere, where it is naturally occurring. But in the mid-1980s, there was the discovery that a different set of man-made chemicals moved all the way up to the stratosphere and started quickly destroying the ozone layer. So it's different chemicals, a different layer of the atmosphere, and mostly over Antarctica. Which then brings us to climate change. And when we're thinking about climate change, we're really focused mainly on gases and particles that heat up the atmosphere, heat up the planet, and change weather patterns. Carbon dioxide is the biggest issue when it comes to climate change. So But that is not an issue for the ozone hole, and it's not an issue for air quality. We can breathe in carbon dioxide, and the levels that we see outdoors, it is really not going to hurt us physically. So to start out, just have us in our minds, these are three totally separate topics. But now let's start to weave them together. We've already seen how drier temperatures, warmer temperatures can lead to unhealthy air pollution here in the Midwest. But historically, when we think about these air quality issues, it's not so much wildfires, but industrial pollution. And really all around the world, as industry has developed and economies have grown and people have driven more cars, our air has gotten more and more polluted. This is a picture from Boston in 1969. Even back in 1969, this was not typical. But today, if you were to go to Boston, you would never see air like this. And the reason you wouldn't see it is because 1 year after this photo was taken, the Clean Air Act was passed. And since the passage of the Clean Air Act in 1970, the major pollutants that are considered as part of this air quality, the health protective air pollution measures, have led to decreases across the board. During this time, our economy has grown, we've driven more, our population has grown, we're using more energy, and for the most part, our carbon dioxide emissions have grown too. So while air quality in many ways is a success story, that success has not carried over to the climate change part of the story. I said that there were a bunch of different chemicals in the air that are regulated by the Clean Air Act. This is showing how each one of them has changed, and this plot goes back to 1990, all the way up until this year. But you see that every single pollutant is coming down. The idea that we can decide to reduce air pollutants, air emissions, and see an effect, we've been doing this since 1970, before I was born. And some pollutants are easier to reduce. Some, it's a little bit more slow and steady. But in many ways, the Clean Air Act has shown us that when we decide to make a change, we can make it. The benefits of these air pollution controls can be measured at the surface, like some of the plots I just showed you. But I love satellite data. And here is an image taken from a satellite that was launched in 2004 called the Ozone Monitoring Instrument. And it can see nitrogen dioxide. And nitrogen dioxide from satellites is one of those chemicals that we can't see with our eyes. It's an invisible gas, but the satellites can detect it. And it's emitted from cars, trucks, power plants, pretty much anything that burns. And you can see here the signature of big cities like Chicago and the Eastern Seaboard, even individual power plants, and if you zoom in, even some big freeways. But this is back in 2005. And just over the past 15 years or so, the air pollution is continuing to get lower and lower and lower. And we can see it very clearly from satellite data. Many cities, NO2 levels have gone down by 50%. So the success story that the U.S. has had has become a role model for the way that countries around the world are addressing the health of their populations and moving toward clean air. And you really can't see that better than when looking at sulfur dioxide, which is a pollutant that primarily comes from coal burning, but it's one where there are technological controls that can be put on and have less SO2 coming out even when the same fuel is being used. And what you're seeing here are each layer is a different part of the world. We're here in North America, which is the light blue. And if you sort of think about the thicknesses of our blob going up over time, we can see that the light blue blob was getting thicker and thicker and thicker until 1970. And then it started getting thinner and thinner and thinner. And Europe got thicker until a couple years later. China was getting thicker and thicker until the early 2000s. So the US led the way, but other countries followed along. And now, around the world, sulfur dioxide is going down, down, down. Sometimes you hear the argument that, well, if we do it, what about the rest of the world? And I would say that when it comes to air quality, we did do it first, back in 1970, and the rest of the world came along too. And so now, across the globe, it's on the downward path. So when I think of the Clean Air Act, I really think of a success story. With the exception of wildfires, air quality in the U.S. has gotten cleaner and healthier since 1970. It's extended the life of the average Wisconsin resident by 1.5 years just since over this time. And around the world, it's viewed as a U.S. success and an example for other countries who are working to achieve cleaner, healthier air for their people. So that's number one. Let's see if we have more success stories. Now I'll take you down to the South Pole, to Antarctica. And what you see here are researchers holding a big balloon. And this balloon is carrying a little instrument that measures the intensity of ozone in the atmosphere. And as you move up in the atmosphere, first you have, in some parts of the world, some human-created ozone near the surface. Then it gets cleaner, but then you get a big layer of naturally produced ozone. And that's what these researchers at the South Pole were measuring when they sent up this big balloon. One way to think about this layer is as a shield that's like sunblock, where we have all the sun coming in from space, but when it hits the layer of naturally occurring ozone, many of the damaging rays are filtered out so that we have less risk of skin cancer, and it's not affecting ecosystems, genetic mutations, things like that. Now, when it comes to ozone, sometimes you hear the phrase, good up high, bad nearby. Because even though it's chemically the same type of gas that we don't like to have at the surface, I often think of it like sunblock. I wouldn't want to drink my sunblock, and I don't want to be breathing high levels of ozone, even though it is a good shield from incoming radiation. So the ozone hole story is really interesting, because back in 1985, there were a group of British researchers called the British Antarctic Survey that were down in the South Pole sending up ozone sondes, like the picture I showed you at the beginning. And they were down right around October and sent up their instruments, and they could not believe what low, low values of ozone they were finding in the Antarctic stratosphere. And actually, when they reported it, some scientists did not believe them back in 1985. And they said this couldn't be possible because NASA has been sending satellites up in space since 1979. And we never saw any ozone hole. Well, as it turns out, I don't know if any of you have ever played around with instruments in space. I worked at NASA in the mid-1990s. And when you have an instrument up in space, it can be hit with solar radiation that can lead to sort of wonky values. And so a natural thing that satellite data processing does is if you see a crazy value, like negative 999 or 1,025,000 or whatever would be considered a crazy value, they throw it out. It's just space radiation. It's just a glitch. So actually, for 6 years, the satellite orbiting the Earth and measuring ozone over the South Pole had thrown out all these crazy values of low ozone that would represent the hole because they thought it was just bad data. But once they went back to crisscross check what the British researchers found, Then they saw that, in fact, the satellite had been seeing an ozone hole, and it had been seeing it consistently since the instrument was launched. So here you see the blue values represent the really low hole over Antarctica, and there it is in 1979, 1980, 81, 82, 83, and you can see it clearly getting bigger, bigger, bigger each year, more blue, bluer and bluer and bluer. 84, 85, this is the year that the British Antarctic Survey discovered the hole. 86, 87, and by 1987, there was a global treaty on the books to protect the ozone layer. When we think about the controversy around climate change, which has been going on since the 1960s, to think that they identified the problem in 85 and solved it 2 years later, that's mind-blowing, really. But actually, and you can see it is persisting. So then you might think, well, if they solved it back in 1987, why do we still have an ozone hole? The chemicals that eat up ozone in the stratosphere tend to live in the atmosphere for decades. 50 years, 100 years, 150 years. So even though we've turned off the spigot, we've pretty much stopped emissions, the ones that are still up there are floating around and doing their thing. So we kind of have to wait till the atmosphere cleans itself out. But there's actually a lot of science that's going into monitoring the ozone hole every year. And you can check it out at Ozone Watch. It's a NASA website. But here I'm giving you the up-to-the-minute latest. This is data as of this morning. The way that the ozone hole works is that it only forms during springtime over the South Pole. You need to have very cold temperatures coming out of the winter. But you also need to have sunlight with the spring. And the only time that you have the very cold temperatures and the sunlight is right around now, October, November, when it opens up. So typically they start tracking it in July, and it gets bigger and bigger through the season. And then by November, now it is declining. And so what you see here is how big it is, and the gray area represents all the values that have ever occurred. So this year, it's right around the middle of its typical size. And this also shows when it is a hole, how deep is the hole. And it gets deeper and deeper and deeper, and then around October, starts moving back. I think this may be an easier way to be looking at the information, where this is showing year by year, back to 1979, the first year where we have data available because the satellite was launched that year. And we saw it getting bigger and bigger and bigger. We could see that ourselves when we looked at those blue dots. Then holding steady, and now it is slightly going down. Similarly, the hole was getting deeper and deeper and deeper and deeper and deeper, and now it's holding steady and maybe going up. So the good news is that the solution is in place. We've turned a corner. The bad news is we have to wait a while for the ozone hole to really show the evidence that it's on the mend. But scientists are tracking not only what is happening with the ozone hole itself, but what is happening with all of those global commitments. Everyone agreed not to emit any more of the damaging chemicals, but are they keeping their promise? And what was really interesting is that some researchers in Australia, and the work was confirmed by researchers here in the US, found that actually there was some groups in China, probably, who were violating the terms of this international treaty. And I want to show you here what we're looking at. The blue line is the sort of scientist's best estimate of how much of this damaging chemical, this chlorofluorocarbon 11. This is one of the chemicals that eats up the ozone layer. that it was going up, 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 up until about 1987, turned around, and then it started coming down, 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 down. Now, the dashed line, the red line, is what they should be doing according to the international treaty. The blue line is what this independent group of scientists sort of backed out, is what is actually happening. The good news is that for many years, what should be happening and what was happening were just the same until the early 2000s. And then researchers started to see that, wait a minute, somebody is violating the rules. Someone is breaking the rules. You can read a lot more about how they came to this conclusion. The good news is it's been corrected, and now they see that that has been stopped, and now everything is getting back on track. And you can also track the abundance of these chemicals in the atmosphere. They were going up and up, and now they are slowly coming down, some faster than others. So when I think about the ozone hole, another success story. It was discovered in 1985. We turned the corner in 1987. But because these chemicals stay in the atmosphere for decades, the recovery process is slow, but steady. I think this also, though, highlights how science can monitor compliance and the results of global policies. And I think that when we're thinking about climate and climate solutions, that should give us a certain confidence that when plans are made, that it's not just taking everyone's word that they're going to stick with the compliance. There's actually checks and balances that are built into the system when policies and agreements are made. Which then brings us to climate change. When I think about climate change, if there's one plot that I can show, this is my favorite plot. And it may be too nerdy, but bear with me because I really like it. It's from a report from the National Climate Assessment, and it was in a chapter called Detection and Attribution of Climate Change. Because one of the most common questions that I hear is, well, how do we know that climate change is caused by humans? Because sure, we can see the temperatures are going up and land is getting drier and precipitation is getting more intense, but aren't there a million possible explanations? And this is why I like this figure. Because around the world, there are about 25 major labs that are focused on trying to understand the climate. And they're understanding it for climate change, to predict El Nino, to understand hurricane tracking, to improve weather predictions. It's all the same toolbox that's being used to try to understand the atmosphere. And these 25 labs or so are all competing with each other. They all want to prove that they have the best computer model. So they get together every few years and really compare in a rigorous way what the different computer models do and which one, what's the variability, how do they agree, how do they disagree. And just to sort of benchmark some of these here in the United States, we have 3 of these big computer modeling laboratories. One run by NASA, based in New York City. One run by NOAA, that's the organization that leads the National Weather Service, and theirs is based in Princeton, New Jersey. And one led by the National Science Foundation in Boulder, Colorado. So these are our premier science organizations that are all even competing with each other to see who can come up with the best climate model. So one thing they do is they say, okay, let's take everything we know about the Earth and about space and represent it in a computer. For example, we know what the intensity of the sun is and solar flares. We know what areas of the Earth are covered by desert and ocean and forest. We know how much carbon dioxide has been emitted going back to the Industrial Revolution. There's a lot we know. And let's put it in our computer models and run those computer models, which, by the way, are not constrained with observations. And then let's see how well they agree with observations. And that's what you see here on the left. The tan, sort of peachy, is the distribution of all the different computer models. And here going from 1880 to 2020. And then what you see overlaid on it this is change in global temperature as simulated by the models. And all of the models show temperatures going up. And then we compare it with observations. And each one of these lines is an observation, a different way of calculating global observations. There's some use satellite data a little bit differently, some correct for the distribution of ground-based monitors differently, but they all show a clear up trend. So the models agree and the observations agree. We can't change the observations. We only have one Earth. But the good thing about these computer models is that they allow us to test what-if questions and use them like a video game. And I don't know if you ever play video games, but sometimes I do. And then you can say, well, what if I were making a reality where there were, only dragons? I can do things like that in my computer game because I can turn things on and off and experience in different conditions. And that's the way that these climate models are. They're like a video game where we can turn off, what if there had been no industrial revolution, no burning of fossil fuels, no human activity? What would the Earth look like then? And that's what you see on the right. And what it's showing is that, they bounce around and they have some extra cool years. These would be when volcanoes exploded. You see those over here too. And you see that for a long time, it was not clear whether the reality that we were experiencing, these dark lines, could possibly have occurred with no human-induced climate change. But somewhere around the 1980s, even all these different computer models, not any of them, could recreate something that looked like the world we were actually living in if they didn't take into account human activity and fossil fuel emissions. If you are interested in this and want to dig more into it, I really recommend all of the science that comes out with this in this climate assessment report. Okay, so the Earth is getting warmer. Where's the good news? Where's the solution? The truth is, when we think about the future, there's certain things we can control and there's things we cannot control. And just like with the ozone hole, we cranked down the emissions, but it's going to take some decades before the ozone repairs itself. And in the same way, when we think about climate, we have the emissions, what we're putting into the atmosphere, and then we have the actual temperature of the Earth. And the temperature is going to keep increasing, kind of no matter what we do. How fast it increases, though, is within our control. And if we take the red line where it's increasing really fast, that's what would happen in scenarios where we keep emitting a lot more stuff into the atmosphere, the red line here. If we take the blue kind of middle of the road line, which keeps increasing and then kind of flattens out toward the end of the century, that's the reality that would happen if we followed the blue line, where we keep increasing for a while, but then make modest reductions through later in the century. The only scenario that's getting it to start flattening out and not keep rising very much is one where we make very significant carbon reductions in the very near term. So the question I'm thinking about is, can climate be a success story too? And I think so. As with the ozone hole and air quality, if we cut emissions, the climate will respond. And the sooner we cut emissions, the less disruption we'll see. So there's a level that many researchers, many experts have been reviewing, and there's a whole report on it, on the 1.5 target. Now 1.5 means 1.5 degrees Celsius warming since the Industrial Revolution. We've already seen 1 degree Celsius warming since the Industrial Revolution. And if you convert that to Fahrenheit, I think in Fahrenheit, that's the 1.5 degree target is really 2.7 Fahrenheit. This plot is also in Fahrenheit. So basically what it's saying is that most experts who are working on this problem, thinking about what's a realistic way to approach it and minimize the damage, say that we should really be keeping this 1.5 degrees or 2.7 Fahrenheit target in mind. And if we compare that with this chart, that means basically we want to get on the green path. We want to get on the green path, which means we have to be cutting emissions very soon. We could be talking a lot more about, well, why 1.5, not 2, not 2.5? What's the difference between the red line and the blue line? This is a infographic from the World Wildlife Federation that's trying to summarize these thousands and thousands of pages of reports. But just as an example, when it comes to like coral bleaching, if we keep it to 1.5 degree warming, then the assumption is that we'll still lose about 70% of the world's corals by 2100. But that's better than 100% of the world's corals if we hit 2 degrees. If you look at Arctic sea ice, it's hard to imagine the North Pole with no sea ice. And if we get to that 1.5 target, we'll expect to see 1 summer every 100 years with no sea ice. But if the Earth warms to the point that it's 2 degrees on average warmer, then we expect to see ice-free summers every 10 years. And we could step through the water availability or extreme weather. For example, even with the 1.5, we basically have a doubling of flood risk. But if we get to 2, then it's almost a tripling of flood risk. So I could linger here and we can come back to discuss more, but basically that's why 1.5 is often cited as the target. Okay, so how are we going to get there? How are we going to be turning the corner and cutting our emissions to get on that 1.5 path? Really, when it comes to thinking about how to get there, it all comes down to where we're getting our energy from. And for the most part, how we drive our cars, how we power our electricity systems, how we heat our homes, how we cook our food, how industrial processes are run, are using fossil fuels. And these include coal, natural gas, and petroleum oil. Petroleum can be used for many things. I think my pants are made out of petroleum oil, as is the carpet here and the contact lenses I'm wearing. But the main thing we do with petroleum oil is we burn it in our engines for transportation. Natural gas is used for both electricity, industrial processes, and most of us heat our homes and maybe cook our food with natural gas as well. Coal is the only one of these fossil fuels that in the United States who is decreasing, and coal now is mainly used in some coal-fired power plants and also in industrial processes. But the non-fossil fuels are the alternative. These are the options of where we could be getting this energy from. And they include nuclear, wind, biofuels, hydroelectricity, and other renewables. For example, tidal energy or offshore wind. So, and wood is a renewable as well. And I always like to think that, back in 1850, we got 100% of our home heating, our home cooking, everything from wood. So is it possible for these non-emitting sources to grow enough to help us turn the corner? And I think so. One amazing story is how solar has become cheap, cheap, cheap. It is now the cheapest way to produce electricity. And it's one reason that here in Wisconsin, there's a lot of solar being installed on rooftops on farm fields by our electricity providers. I was just talking with Alliant Energy in the atrium about some of their solar projects as well. And the reason why solar is booming is because the price has come down. A colleague of mine at the University of Wisconsin, Greg Nemeth, he actually wrote a book called How Did Solar Get So Cheap?, where he was interviewing industry leaders all around the world to try to understand what aspects of the technology, the engineering, the business drove it down. I didn't read the book, I gotta confess, but I know that it's a complicated story because you look at this, and even from the labor cost to the hardware, it's all coming down. The other big issue when it comes to whether it's electricity powering our transportation systems, or more wind, or more solar, is how do we store the energy? Because we only get wind when the wind is blowing, we only get solar when the sun is shining, so you need to have storage systems. But the good news is, the price of these storage systems has also been coming down. And just in this 3-year period from 2015 to 2018, they've gone down by nearly 70%. So this then is, no more graphs. This is bringing me to what does this mean to you? And it was mentioned during the intro that I'm a member of this group called the Science Moms. And one of the reasons why I joined this group is because I had gotten asked so much, well, what does this mean for me? And what does it mean for my family? And it's been really a pleasure to be working with this national group who's been really trying to develop videos and messaging and clear talking points to be resonant with the public, not just moms, but moms were an audience that had not been served by previous science outreach initiatives. And in many households, a lot of the purchasing decisions are made about moms, and when we're made by moms, and when we're thinking about the future and why we care about climate, a lot of us moms are already thinking decades down the line for the well-being of our kids. So the Science Moms group, it's a nonpartisan group of mothers who are also climate scientists, and the goal is that we are breaking down climate into digestible parts. I'm on the list, as are a lot of colleagues of mine who I work with in science and have worked with for years. Dr. Marinoff is a professor at Penn, and we went to grad school together, and Emily Fisher did her PhD at the University of Washington, and I've known her for over 20 years. And so these are all folks, we serve on a science board together, who are well-respected, well-known scientists who are out there trying to be a accessible point of contact on this complex issue. So one of the science moms, Joellen Russell, she was in some funny videos, but really aiming at this idea of, like, can we break the personal actions on climate change down into a to-do list? Because moms love to-do lists. And the to-do list is to 1, swap, 2, share, and 3, speak up. And this is a good excuse for me to show pictures of my 2 little guys, Peter and Henry. So when we're talking about swapping, the idea is to, when you're making major purchases, to think about making, moving more polluting systems to cleaner systems. These are not everyday purchases. We are not all going out and buying a new stove. But when getting a new vehicle, consider an electric vehicle, because electric vehicles can be powered by any of those non-emitting energy sources that I mentioned earlier versus gas in the tank. When purchasing new stoves or heating systems, consider electrification for the home, and where you have the option of getting your electricity from clean sources, supporting the utility efforts to move toward a cleaner electric grid is part of the solution. And so, one way to think about this swapping out is that if we want to be getting our energy from non-emitting sources, then the idea is to move as much as we can to electricity and then move the electric grid as much as we can to non-emitting sources. Sharing information. There's been a lot of research about how climate change is an issue that's on people's mind. It's a concern about the future, and yet we don't talk about it, maybe because it's become too political or too controversial. But the more that we can share facts, concerns, and solutions in an everyday part of our life, that has really emerged as one of the most powerful things we can do to solve the climate problem. And, of course, our leaders play a big role in moving forward the kind of large agendas that have been successful for air quality, that have been successful for the ozone hole, and the kind of things that will be needed for climate change. So whatever perspective you're coming from, engaging with leadership to let them know that you care about this issue. So when I think about what a climate success might look like, I really like to think about turning the corner. We're not going to snap our fingers and have climate change go away. But just like in 1987, they put in place changes that have us on a path to solve the ozone hole, and in 1970, they put us on a path to continuously improve our air, I think that we could be on a path to be solving climate. I would like my kids to be looking back at the 2020s and think, wow, that's when they turned the corner. That's the time that they made the change that is helping us get back on track today. And beyond thinking about the emissions, there's also this idea that the climate is changing, and planning for making choices in our lives and businesses and development that recognizes that the climate of the past 50 years here in Wisconsin is going to be different than the climate of the next 50 years. And so tapping into the best available science that we have. And I noticed in the atrium, the Wisconsin Initiative on Climate Change Impacts has a table. They have a great website, and they're doing a lot to issue publicly available Wisconsin-specific projections to support decision-making on what weather variables, precipitation, snowfall, that kind of thing might look like across the state. And I think talking about solutions that make sense to you. Nobody has to buy into some ready-baked plan. This is something that cuts across all aspects of our society, and I think it's really important for everybody's voice to be part of the conversation. Here in Wisconsin, we do not mine coal. We do not have any natural gas. We do not have any oil wells. So we actually don't have any fossil fuels coming from the state of Wisconsin. So as this is moving to, aside from studies showing that renewable energy resources can create jobs in general, there's a lot of opportunities specific for Wisconsin, and opportunities, as with many other environmental challenges, for U.S. to lead the way. So with that, I'll stop. I'm excited to answer questions and really appreciate all of your time and attention this evening. Thank you. So happy to answer questions. Yeah.
I'm curious, I've heard that I can't remember if it's nitrogen oxide or if it's sulfur oxide. One of those actually has a cooling effect on the planet, and that power plants are shutting down, phasing out of them, that we actually might see a slight increase in temperature just briefly while that transitions. I don't know if you know more about that.
Yeah. So the main warmer of the atmosphere is CO2, but that's not the only story. There's a lot of other warming gases, and there are cooling particles. And so there's sort of an area of research about short-lived climate forcing. So if you ever want to Google it, short-lived climate forcing. And there are some of these air pollutants that we've been regulating for public health that warm the planet. So as we clean the air, that's good, we're getting an extra one. But sulfur dioxide, and another one is organic carbon, which is kind of the white, light gray smoke. Both of those are cooling. And sulfur dioxide, not directly, but it reacts to form little particles called sulfate particles. So it is true that as we reduce these in the air to protect public health, we will expect to see a little bit of a warming signal, which we're already seeing in areas over the U.S. because we've been successful at cleaning up our air. I think, so you're totally right. The good news, though, is that whatever sulfate is in the air is this is not something near the surface that is something to be like, oh, well, maybe we should just load it up more to cool the planet, because that's something where it doesn't last very long near the surface anyway. But from time to time, when there's a really powerful volcano, and volcanoes emit a lot of sulfur dioxide, and if it's not every volcano, but really powerful volcanoes shoot all the way up to the stratosphere. And when they're up in the stratosphere, then it releases the chemicals above the clouds. And then they don't rain out because they're above the clouds, and they can stay in the atmosphere for months. So sometimes when I was showing you that plot and I said, well, sometimes it was cool, and I said those are volcanic emissions, it's because of the same cooling aerosols that you're mentioning here that got trapped in the stratosphere and actually had a major cooling effect on the atmosphere for a year or more. Yeah.
So I'm just very glad that you brought this up, because I'm very worried about the climate, and I'm particularly worried that it's going to be more than 1.5 degrees, maybe 2 degrees, and it's going to stay hot for a long time. So what do you think about voluntarily or purposefully putting particles in the stratosphere?
Yeah, so there's this whole category of ideas that are collectively known as geoengineering. And putting particles deliberately in the stratosphere is one idea where you're like, well, that could be a way to cool the planet. Some folks have suggested putting mirrors up in space so that less sunlight hits the Earth. Some folks are looking at kind of fertilizing the oceans so that they take more carbon dioxide out of the ocean. There's a lot of ideas. And I guess my personal opinion is like it's good to have all the options on the table. But we don't know enough now to charge forward with any of these options. And the truth is that like the sulfate in the stratosphere that happens with a volcanic explosion, that is really harmful to agriculture, food supplies. I mean, this is not a good cooling situation. Now, if we were totally in control of it, we could probably tune it the way we want, but there's just a lot that we don't know about the climate system. So this is an active area of research. The National Academy of Sciences just came out with a report on geoengineering. There are serious researchers doing serious work on this, and a lot of serious startup companies who see this as the future. So, you know, I'm kind of agnostic because there's not one great solution that we're ready to get behind, but certainly it's good that people are looking into it. Yeah.
I think I heard in the last week or so that the area of the ocean where the North Atlantic current keeps the United Kingdom warm and keeps southern Scandinavia warm is heating up more, or is that an issue?
Yeah. So it's a great question. So one of the, maybe I'll start big and zoom in on your question. One of the programs that I'm in at the University of Wisconsin-Madison is called the Atmospheric and Oceanic Sciences Program. This used to be called the Department of Meteorology. But back in the 1990s, it was becoming clear that what was happening in the atmosphere was fundamentally linked to what was happening in the ocean. And you really couldn't study one without studying the other. And so that's why really across the U.S. and around the world, a lot of academic programs started relabeling themselves as atmospheric and ocean sciences. And this gave them the toolbox to tackle problems like El Nino and to understand why Europe is so nice and warm, even though actually it's at a higher latitude than cold climates in North America. But it's also helped like us understand, or at least this is how I got understanding. I'm not an oceanographer, but I've had to take classes through these types of programs, that there is a circulation going on in the ocean, sometimes called the ocean conveyor belt. And that this ocean conveyor belt is circulating in a way that fundamentally affects weather patterns on outside of the ocean, everywhere. And the engine of this massive conveyor belt is the North Atlantic. It's called the North Atlantic Deepwater Formation, where you have really cold water that is very heavy and sinks, and that drives the conveyor belt. And so one of the great concerns about climate change has been that if you're warming the planet, is that North Atlantic water going to be cold enough to sink? And if it's not cold enough to sink, what happens to the conveyor belt? And if the conveyor belt stops circulating, what happens to weather patterns that we have grown familiar with? And actually this was taken to a totally unrealistic extreme, the basis of a early 2000s sci-fi movie called, what was it called, The Day After Tomorrow, or so, where you had snowstorms blanketing the Statue of Liberty. So, but in all seriousness, researchers are finding that under some versions of a future climate, you see the possibility of that conveyor belt turning off. And I had not heard that there was actually observational evidence that that was happening, but that is consistent with how the facts could line up. Yeah. Yeah.
You mentioned the idea that we should try to electrify our homes. It could be panels, switching to an electric oven. Can you tell us, we can't do it all. There's cost limitations.
Oh, yeah.
Is there one thing you'd pick, like, this is the one thing I'd like you to do if you can?
So it's a great question. And I'd say, I think where we are with electric vehicles is further along than where we are with electric homes, especially in a cold climate like Wisconsin. One of the issues that we're dealing with homes is that, we use natural gas mainly, I would say, for two things, but I'll throw in a third. One is heating our homes. Two is stoves. And I really like watching cooking shows. And on the cooking shows, the fancy chefs, they all use a gas burner. And so as we're thinking about could we move away from natural gas, most of us don't really care what fuel is keeping our homes warm as long as the homes are warm. But we do care about whether we can cook like the chefs on TV. At least I do. And so I think that there's a lot of focus on people's choice of stove. Because I think there's the feeling that if the great we, can make people happy with electric stoves, then they will be willing to change their whole heating system away from natural gas when the technology comes along, when it's cost effective, etc. But if you're married to your gas stove, then it doesn't make sense to have electric heating if you still have a gas line coming into your stove. So there's a lot of focus these days on emphasizing the value of electric stoves. And I'll say, we replaced our stove and our heating system back in 2018. And way back then, people were not talking as much about electrification of home heating and cooking. So we got a new stove and we got a new natural gas heating system. And to your point about the costs, we're still using them. We're not getting rid of them. I think, though, it's this idea of when the time comes to make the choice. If I were buying it today, I would buy an electric induction cook stove. And, I've heard they're really cool. My mother-in-law just moved, and the house that she moved into has an electric induction cook stove, and she was disappointed because she had to get rid of some of her pots that didn't work on the stove. But so far, she loves it. And I've heard it boils water in like 60 seconds. So I think one issue is that some of these changes are not sacrifices, but are actually like amazing new technology. And so I think that as a long answer to your short question, I would say if you're replacing your stove, go for a electric stove. And if you're replacing your car, consider an electric vehicle. And if you're replacing your furnace, consider a heat pump. Sort of consider whichever one it's coming time to replace. Yes?
So all of our consumer behavior has an impact on climate change. And that's probably not the place where your research is. But it just feels like there are ways, changes that individuals can make. But then there are folks who say, oh, no. Industry has to do it. Our individual choices don't make any difference. This is a fight I have with my sister. Because we do a lot of changes in our lives that are focused toward reducing our climate. So can you say a little more about any of that?
Yeah, you're hitting on a really great issue. And, there are things that we can all do in our day-to-day life. But if we look at where our electricity is coming from, most of us don't control that. And if we need to drive a car to get from point A to point B, most of us can't re-outfit it in our garage. And so, I would say it's, everyone has to move forward on the path that makes sense to them. I think a lot of us like to do things that make us feel good about our place in the world and the way that we're living our life, but nobody's perfect. I mean, I know, for example, that it is healthier and lower carbon to eat vegetarian. But I love cheeseburgers. I can't help it. And so I think that there, is this idea that that this is just my opinion, but I think that leading with the idea that everybody has to sacrifice things they love, like cheeseburgers, might be alienating. Okay, I know. But I think that this is the thing. I feel like everyone needs to have their path, and make their own choices and feel supported doing that. Certainly, there's the idea of, being, living what you believe, and this idea of sharing your perspectives and sharing your ideas is something that's easier to do. If you're like, oh, I'm biking today because I want to reduce my carbon footprint. But I want to say, even if you're not biking, even if you're not eating vegetarian, you can still be part of the climate conversation and still be part of the solutions moving forward. And this is something that I really feel myself that, if everyone sees that climate is a big issue and wants to talk about it and wants to make a change, we probably would move faster. But some people might just say, I really like that the induction cook stove boils my water so fast and I don't have to worry about my kid getting burnt. Or they might say, those Teslas, they look really cool. And or I would like to have more jobs here in Wisconsin and make more investment in renewable energy and not be sending as much money to other states or to other countries. And in my opinion, like all of those are moving in the same direction. And so just this idea of supporting everyone versus sort of having, it become a competition about which idea is better. Because I would say both you and your sister are right. And I'll say I am a middle child, so I really like to have everybody happy. So, yeah. Oh.
You mentioned the role of governments and international bodies to work together to turn the corner, and how, in the example that you gave of the Clean Air Act of 1970, how the U.S. led the way. Who do you think the leaders are now in the world?
Well, it's a great question. Certainly Europe is ahead on prioritizing actions on climate. And I would say China is ahead on investments in renewable energy and producing solar panels. But, you know, there was, I think it was the Focus on Energy booth outside, Brady, who has a lot of information on the tax incentives from the Inflation Reduction Act and the Biden administration, and trying to make the clean energy choices more cost effective, that things are catching up. So, you know, I would say that right now the U.S. is not the leader in climate solutions. I mean, that is true. And I think it's more controversial here than it is in most other countries. But we could be. Yes?
I kind of want to dovetail on that and to express that in so many slides that you showed, it is the Clean Air Act that brought all those, our air quality to what it should be. And is it really realistic? Yes, we should and must do all we can as individuals. But the very most important thing is federal action. And to that effect, when we've got a fossil fuel lobby that controls a lot of what goes on in our country. But unless there's a grassroots movement for people to demand climate action, all of our little things, they're needed too. But they can't do nearly what, for example, a tax on carbon could do. And I don't know if people are aware of it. Over the years, over 3,500 American economists have signed a statement saying that the carbon tax is the most effective and fairest way to address this problem. So I encourage people to talk to their congressmen and the leaders in Washington and do everything they possibly can to pressure the movement for a tax on carbon. And a tax on carbon doesn't have to hurt ordinary families. In fact, many of the projections show that a tax on carbon, even though the prices for gas and heating fuel will be higher, of course, that the dividends that will be returned to the American people in a carbon fee and dividend type program will more than offset those increases in heating costs and the price of gasoline. So I just want to put it out there. I'm with Citizens Climate Lobby, and I strongly encourage people, yes, do all those things. And along with those, I would say reduce unnecessary air travel and consider limiting your meat and eating plant-based diet. Those are very, very crucial things.
The Citizen Climate Lobby has a booth.
Are you all concerned about the carbon footprint of all these batteries for these cars, whether it's the manufacturing or the eventual disposal that no one talks about?
Yeah, so, you know, I think that there's, climate is not everything. There is water issues, there's disposal issues, there's rare earth metals issues, there's where they're being mined, how they're being mined, there's child labor, all of that. If we are thinking just of carbon and just of energy, there is accounting for the production and the disposal as well as the life. And this is sometimes called life cycle analysis or cradle to grave analysis. And that has become the industry standard in thinking about, is a solution really better? So how do you compare an internal combustion car versus an electric car? How do you compare an LED light versus an incandescent light? And those studies show that sometimes it does take more energy to create them, and it does take more energy to dispose of them, but what you're saving over the lifetime, the use of it, is a net win. So there is discussion about these different issues, and there's accounting for it in the analyses that are being done to sort of say, like, whoa, we don't want to overlook these issues. Now, sometimes, though, we're comparing different goods and bads that are hard to compare. And a good example is, like, even if you go to the grocery store, paper or plastic. And, well, it takes more water to make the paper, but the paper may be more recyclable than the plastic. But if they go to a landfill, then the plastic is better. I mean, there's no easy answer, which is why they keep asking us in the grocery store which one we want. And part of it is like, well, if I can reuse the paper bag a few times, and then maybe I'm saving something else. I don't know. But, I think this idea that it's not necessarily one versus the other, but I'd say that within the kind of engineering methods that are used to sort of put these out apples to apples, the production and disposal are included.
It's a battery for an F-150 Ford Lightning, weighs 1,000 pounds. That's not a small battery.
No. And, I think one thing that the battery technology, we are in the infancy of this battery technology. This is a huge growth area. And one of the things that they're looking at, actually, there's a startup company in Milwaukee that was saying, the car batteries are so much bigger and cheaper than almost any other type of batteries. Can we kind of bundle these together to be providing utility scale options for increasing solar or increasing wind? So, I think how the battery technology is being driven, though, is partly by where is the demand and where is the market and where are the factors that are going to be driving it to, think about how computers used to take up a whole room and now we can carry it around in our pocket, So I think that there's no question, we're not, at the point today that we could snap our fingers and have every vehicle electric. But the batteries are getting better and smaller. The cars are getting more cost effective. There are more charging stations around. The charging stations are getting faster. Yes, it does. Yeah. But it also comes as a savings. There's things that we don't have to do that we might have done before. And, even electric vehicles. My husband, back in 2019, he really wanted to get an electric vehicle. And I drive a Prius, but I like being able to go to the gas tank, fill it up. I know exactly how much is in there. It is easier. But just in the time that we've had his electric vehicle, it's gotten easier and easier and easier and easier to charge it. And so now we take the electric vehicle on all of our trips because it's just a nicer car to drive. And then, we do have to plan out where the charging stations are going to be, but every month there's new charging stations available. So, I think we're going through these changes that if you had asked me 5 years ago, 10 years ago, I wouldn't have believed it. And I think that the changes that are happening are going to make 5 years from now and 10 years from now quite different than they are today. So I think, part of it is sort of figuring out, how can we position ourselves to benefit from the changes that are already happening, and how can we be in a position to help advocate or support the changes that we want to see. And that's going to be different for everybody. In the back, yeah.
Okay. I always like to ask climate scientists their thoughts on population. And with your optimistic presentation, I'd like to hear your thoughts on how impactful that is, and if you think these technology advancements can kind of balance out those scales of population decline, and just kind of where your stance is on that.
Yeah. So, if you're thinking about the total emissions from any community, it's sort of, how many people are there? How much energy are they using? What is the carbon or other emissions per energy amount? And that leads to kind of three knobs that we can turn. One knob is population, but that's really complex. And in many parts of the world, population is not rising anymore anyway, and it's slowing down. The next knob is how much energy we're using. And in the United States, we use way, way more than other countries. And not just countries that we might think of as less industrialized or less developed. In Germany, we use about twice as much as the typical German family. And they have very good food, and they drive nice, fancy cars, and they have access to the same Netflix shows that we have. But they tend to live in somewhat smaller dwellings. They don't dry their clothes in dryers. They usually hang them out to dry. They have slightly smaller refrigerators. There's just slightly different changes that add up that we have twice as much energy use as they do. But really all of this then comes to the third knob, that if we're getting our energy from non-emitting sources, then we can use however much we want, and we can have as many people using it without bumping into a problem. So I guess I would say that that I don't really think very much either way about population issues, because there's so much more to be gained on cleaning up the energy supply that we have, and increasing efficiency, making our cars drive more on each charge that they get. I mean, all these things to make the energy we have go further, and the energy that we need to use be cleaner. Yeah.
So I'm actually in the food biography class here on campus, and it's kind of amazing to learn about just kind of how the world works and everything. So I've done the last couple months. I guess my question is, based on even just talking to my own family and stuff, what do you think scares people so much about change in terms of like proactive change for climate change? Do you think it's like change is scary? Do you think it's like we don't want to have to learn new things?
Well, there's actually been a lot of research on public attitudes about climate change, and there's a famous study that came out of Yale University where they talked about the 6 Americas, where different parts of the American public kind of position themselves in different groups that see the issue quite differently. And I would say, I'm not even going to ascribe to 6. I would say that there's probably, as many perspectives as there are people walking on the street. If you were to ask them their perspectives on if they want change, if they don't want change, even in this room, we've heard perspectives of even folks who may agree on the outcome but have disagreements of how to get there. So I would say, that to me, again, like I tend to be a middle of the road person. I'm motivated by the facts. I'm an optimist, and I feel that there's been a little bit too much emphasis on all the things we'd have to give up to achieve a climate solution. And I think, if you people look at their house or look at their car or look at the life that they led when they were kids and thinking about, their own, what they want their life to be like, and if they feel like it's all about sacrifice, then I think it is hard to rally around that idea. Because for sure, 100% reducing air travel is 100% the way to reduce your own carbon footprint. But, if someone's been saving for a big trip to Hawaii and then you tell them they're not allowed to take it or that they have to feel guilty taking it, that's not necessarily something that makes them excited. So I think that, I personally like to find ways to bring people together to say, okay, we can disagree on what we should do, but maybe we can find things we agree on as to start the conversation, or at least to say, let's talk about it without fighting. Let's talk about this without it becoming an awkward Thanksgiving dinner. Because, if we can't even talk about it, then it's hard to actually solve a problem. And I think there's a lot of complex problems that we've solved as a state and as individuals and as a country and as the world. I mean, well beyond the complex problems in this talk. And, I feel like if we can at least just talk about what the problem is and what are different pathways forward, that's one way to open the door to real solutions.
We do like all of this stuff. Is there a reason? You're very smart, like Coach Joe Leedy.
Yeah.
Is there a reason why that the chefs on TV keep continuing with gas stoves instead of using electric?
Well, as an amateur chef, I will say, with a gas-fired oven, is that, if you turn off the heat on your gas stove, then there's no more heat going into the pan, whereas with an older the kind of electric stove that I had before, you'd turn it off and it would still be hot. And sometimes you'd turn it off and you'd forget and you'd accidentally touch it and get a super bad burn. Like, not good. But with these induction cook stoves, which, to be honest, I have not cooked on, but I have heard from my mother-in-law and on cooking podcasts that they, one, turn off the heat instantaneously, and they don't get hot to the touch. So some of these problems that people associate with electric stoves aren't problems with the new generation of electric stoves. But how to, make all these changes, change is difficult. And I think, it can be easy in the abstract, but once you start doing things in the way that you like, that you've gotten used to, that you've been trained in, or that your parents were trained in, or that you associate the way your grandparents did things, it's just not easy to force change. So I think part of it is sort of getting buy-in on the upsides of change and what can be good for different people in different ways.
Tracy, would you be willing to talk to folks individually a little bit?
Sure. I'm happy if anyone wants to talk one-on-one. And just, again, thank you all so much. It's been a real pleasure.